Hello everyone, welcome back to my VLSI diary. My name is Shivangi Upadhyay and today we are stepping into one of the most important foundations of VLSI design, which is RTL and hardware description languages. If you have understood digital electronics from the previous videos, now it's time to convert that knowledge into real hardware implementation. In this video, we will explore what RTL design actually means, why it is used in chip development, and how languages like Verilog and VHDL help us to describe hardware at the register transfer level. So, whether you are just beginning your design journey, preparing for VLSI interviews, or planning to work on FPGA and ASIC projects, this session will give you the clarity that you need before writing your first lines of RTL code. So let's get started. Let's begin by understanding what RTL really means. RTL stands for Register Transfer Level and it is one of the most important design abstraction level in digital VLSI. At this level, we do not describe the circuit at the transistor or gate level. Instead, we describe how data moves between registers and what logical operations are performed on that data on every clock cycle. In RTL, the design focuses on mainly three things, which is the registers that holds the data, the operations which performs on the data, and the control signals that makes these operations happen over a time. The great thing about the RTL is that it is both abstract and synthesizable. This means that even though we write it in Verilog or VHDL in a human readable form, the synthesis tool will automatically convert it into actual gate level hardware. A synthesis tool converts the RTL code into a gate level hardware design that can be implemented on FPGA or ASIC. Basically, a synthesis tool is like a virtual manufacturing environment for a chip. RTL is widely used in real chip development because it is easier to simulate and verify. It allows early detection of design bugs and it helps designers optimize the circuit for performance, power, and area before fabrication. So, at a high level, RTL is the bridge between digital design and ideas and real hardware implementation. And it is the starting point of almost every modern digital chip. Now, let's talk about why RTL design is so important in modern VLSI. RTL or register transfer level is the foundation of digital hardware design. This is the level where we describe the how data moves between register and what logic operations are performed on every clock cycle. The biggest reason RTL matters is that it allows fully automated synthesis. This means the Verilog or VHDL code we write can be converted directly into the gate level hardware using EDA tools. Instead of manually drawing the circuit, the tool does the optimization for speed, power, and area. RTL also forms a crucial bridge between algorithms and real hardware. If we design a digital systems like UART, processor control logic, or an ALU, first we write the algorithm, and RTL is the stage where that algorithm becomes a real hardware description that can be fabricated onto silicon or implemented on a FPGA. Another benefit is modularity. RTL encourages breaking the system into smaller reusable blocks, commonly called the IPs. For example, an adder, FIFO, UART, memory controller, or state machine can all be developed once and reused across multiple projects. This makes design faster and more scalable. And most importantly, RTL allows early verification and bug detection. We can simulate the design even before hardware exists, catch timing or logic issues early, and fix them before fabrication, which saves a huge cost and time in the chip development process. So, RTL is not just a coding step, it is the blueprint that guides the synthesis optimization, verification, and finally real digital hardware implementation. This slide introduces two important languages used in digital design, which is Verilog and VHDL. These are known as hardware description languages or HDLs. Unlike normal programming languages that describe software, HDLs are used to describe digital hardware circuits. This means that instead of writing instructions for a processor to execute, We describe how flip-flops, logic gates, registers, combinational logics, and data path behaves. SGL allow us to design hardware at different abstraction level, including register transfer level, which is commonly used in FPGA or ASIC developments. Verilog is one of the most widely used language in the semiconductor industry. Its syntax is very similar to the C programming language, so engineers coming from software background often find it easier to learn. Verilog is compact, industry friendly, and heavily used in commercial chip development. VHDL, on the other hand, has a syntax based on ADA. It is strongly typed, which means it forces more structure and type checking during coding. This makes it highly reliable and preferred in applications where safety and correctness are very important, such as aerospace, defense, and automotive systems. Both Verilog and VHDL can be synthesized, which means the code written in these languages can be converted into real hardware using tools like synthesis and place and route. Apart from design, these languages are also used to write test benches which help simulate and verify the logic before actual hardware implementation. In summary, Verilog and VHDL are the foundation of digital hardware design, helping engineer model, simulate, verify, and finally implement real hardware logic on FPGA or ASIC platforms. The key difference between Verilog and VHDL is both are hardware description languages used to describe digital circuits, but they different in syntax, style, and uses. Starting with Verilog, it has a syntax similar to the C programming language. This makes it compact, easier to write, and faster to learn, especially for engineers with software background. Verilog is widely used in the semiconductor industry for commercial chip and FPGA development. Its coding style is more flexible, but at the same time, it allows the designer to make mistakes more easily because the language is not as strict. On the other hand, VHDL has a syntax derived from ADA, which makes it much more structured and strongly typed. This means the language forces the designer to define everything clearly, such as the data types and the signal declarations. Because of the strictness, VHDL helps reduce design error and improves reliability. This is why VHDL is commonly used in safety critical industries like aerospace, defense, and automotive. In terms of readability, Verilog code tends to be shorter and more concise, while VHDL code is longer but more descriptive and self-documenting. Finally, both languages are synthesizable and can be used for RTL design and test benches. The choice between them often depends on the industry domain, project requirements, and designer preference. So, in summary, Verilog is the industry friendly, compact, and fast to write, whereas VHDL is strict, detailed, and preferred when safety and reliability are top priorities. Now, we will discuss the key building blocks of RTL design. Register transfer level describes digital hardware in terms of data flow between registers and the logic that processes that data. The first component is combinational logic. This includes logic gates, adders, multiplexers, comparators, and any circuit whose output depends only on the current inputs. There is no memory involved. Typical examples include arithmetic units and Boolean logic. In RTL design, combinational logic defines how data is processed at each clock cycle. Next is sequential logic, which adds memory into the system. Sequential circuits depend on the past states as well as current inputs. This includes flip-flop, counter, and registers. Sequential logic helps the design retain state information across clock cycles. One of the most fundamental sequential element is register. Registers hold data temporarily and transfer value only on a specific clock edge. In RTL, the movement of data from one register to another through logic is what gives the name register transfer label. Building larger systems require connecting multiple register and logic blocks. For this, we have the data path and control path. The data path performs operations such as arithmetic shifting, comparisons, and data movement. And the control path generates the signals that decide what action should happen. For example, which operation on the ALU should perform or when data should be written into a register. The control logic often uses state machines. This brings us to finite state machines. FSMs are used to control the behavior of sequential circuits based on different operating states. FSM ensures that digital hardware operates in predictable sequence like waiting, processing, responding, and returning to idle. FSMs are widely used in protocols, controllers, interfaces, and data sequencing. In RTL design, timing is critical, so we need to understand setup and hold time and general clocking considerations. Setup time defines how long a signal must be stable before the clock edge, and hold time defines how long it must be remain stable after the clock edge. Violating these timings can lead to metastability and unreliable behavior. Managing timing closure is one of the most important tasks in professional chip design. Finally, every digital design needs a reliable way to initialize internal registers and states. This brings us to the reset strategies. A reset brings the system to a known starting state. We have two main types, which is synchronous reset, where the reset works only with the clock edge, and asynchronous reset, where works immediately independent of clock. Each approach has its own trades-off in terms of reliability, timing, and area. So, in summary, RTL design is built from combinational and sequential logics, registers that hold data, data path and control circuits that define functionalities, FSMs for structured control, timing rules for correct operation, and reset strategies to ensure predictable startup. Together, these components form the backbone of modern digital hardware design. Now, combinational logic is one of the fundamental element of RTL design. This type of logic has no memory, means the output depends only on the current input at that moment. There is no concept of storing information from the previous clock cycles. In Verilog, we typically describe combinational logic using the always at the rate star block. The asterisk indicates that the block should reevaluate whenever any of the input signal change. This ensures that the output always reflects the latest input values, just like real combinational circuits. Another common way to model combinational logic in Verilog is the continuous assignment using the assign keyword. This method is especially useful for simple logic expressions such as multiplexers, adders, or bitwise operators. Continuous assignment are evaluated continuously just like a physical wire implementing a logic function. One of the important rule when designing combination logic is that we must avoid the unintentional creations of latches. Latches are unwanted memory element that occur when not all output signals are assigned in every possible code path. This typically happens when an if statement is missing an else, or a case statement does not cover all possibilities. Latches can cause unpredictable timing behavior and may lead to synthesis and functional issues. Therefore, combinational logic in RTL should always ensure that for every input condition, the output is fully defined, preventing accidentally memory interface. Proper coding practice like complete assignments, default cases, and full coverage of conditions helps maintain efficient, reliable combination logic. So, in summary, combinational logic models instantaneous data processing using always at the rate asterisk block or assign statements. And care must be taken to the ensure no unintended storage element are created. Now, sequential logic is the second major part of RTL design, and unlike combinational logic, it has memory. That means the output not only depends on the current inputs but also on the past states of the system. In Verilog, sequential logic is typically described using an always at the rate pauses clock block. means the logic updates on every rise edge of the clock. This models real hardware behavior where data is captured into flip-flops synchronized with the clock. Because sequential elements store values from one clock cycle to next, we must also provide a proper reset mechanism which initializes register to a known state when the system starts. Without reset, flip-flops may power on with unknown values, leading to unpredictable behavior. Resets can be synchronized, which active on the clock edge, or asynchronous, which apply immediately. Inside sequential block, we use non-blocking assignment, which allow all the register update to happen in parallel, just like real hardware. Using block assignments in sequential logic can cause simulation synthesis mismatches or race condition. So, non-blocking assignments are the standard for register-based design. Sequential logic forms the backbone of the digital system, implementing registers, counters, state machines, control logic, and pipelines. It ensures that the design processes in controlled and timed manner from one clock cycle to next. So, in summary, sequential logic captures data using flip-flops on the clock edge, requires proper reset handling, and uses non-blocking assignment to accurately model the real hardware behavior. In digital RTL design, a system is usually divided into two major parts, the data path and the control path. Understanding the difference between them is essential for clean, scalable, and easy to verify hardware design. The data path is the section where all actual computation happens. This includes arithmetic and logical operations performed by blocks like ALUs, shifters, adders, comparators, multiplexers, and registers. The data path moves from data from one register to another and performs processing on that data every clock cycle. In simple terms, the data path is the part that does the work. On the other side, we have the control path, which decided how and when the data path should operate. This is typically implemented using a finite state machine or FSM. The control logic generates the enable signals, select lines, operation modes, and timing signals that guides the data path step by step. So, while the data path performs the computation, the control path tells it what to do next. Separating the design into data path and control has many advantages. It keeps the RTL organized, improves readability, enables modular reuse, and makes verification significantly easier because each half can be tested independently. The data path can be validated with stimulus, and the FSM can be verified with state based test scenarios. This approach is widely used in processors, DSPs, communication controllers, and almost all complex digital designs, where computation and decision making need to be cleanly structured. So, in summary, the data path is where operations happened, the control path decided the sequence, and together they form the complete hardware behavior of the system. Now, finite state machines or FSMs are one of the most important elements of digital design, especially when building control logic in RTL. An FSM is used when the operations of digital circuit depends not only on the current input but also on the history of previous events represented by the current state. In RTL design, there are mainly two types of FSMs, Mealy and Murray machines. A Mealy machine produces outputs based on both the current state and current input. Because of this, the output can change immediately when input changes, making Mealy machine faster but sometimes harder to debug. And a Moore machine produces output based only on the current states. This generally leads to more stable and predictable output, though it may require one extra clock cycle for some operations. To design a FSM, we must define a few components. First, states. These represents different condition or modes of operation of the system, such as idle, read, or process. Second is inputs. external or internal signal that triggers state transitions. Third is outputs, the action or signal driven based on either the state mole or state plus input melee. And fourth one is state transition, the rule or condition that describes when the FSM moves from one state to another. In Verilog or VHDL, FSMs are usually implemented using two or three always blocks. One block for sequential logic, which stores the current state using flip-flops. One block for combinational logic, which determines the next state. Optionally, a third block to generate outputs depending on digital design style. FSMs helps organize control logic clearly, improves readability, and make the circuit easier to simulate and verify. They are widely used in protocols, communication blocks, controllers, and decision-making logic in the digital design systems. Now, let's look at some essential RTL coding guidelines that every digital designer should follow. First, always use non-blocking assignment for sequential logic because it ensures correct parallel update of registers. For combinational logic, use blocking assignments for clean order behavior. Next, avoid unintended latches by making sure every output in a combinational block is assigned in all possible conditions. Use synchronous reset as it improves timing predictability as consistency across the design. Also, always use clear and meaningful signal names, making it easier for others to understand and verify your design. Another key point is to write synthesizable RTL, that means avoiding simulation only constructs such as delays, initial blocks in ASIC designs, and unnecessary behavioral code. For example, a simple D flip-flop can be written as shown here, using a positive edge clock and a non-blocking assignment. Finally, RTL development and synthesis can be carried out using industry standards tools such as Vivado, Design Compiler, Quartus, or Cadence Genus. RTL design is the backbone of digital VLSI system. At this stage, we are no longer just writing code. We are describing real hardware that will exist on silicon. HDLs like Verilog and VHDL allow us to convert ideas into logic circuits made of flip-flops, registers, combinational path, and sequential elements. That is why understanding the fundamentals of digital electronic, combination logic, sequential logic, timing, and state machines is absolutely essential. RTL acts as a bridge between algorithm and physical hardware implementations. When we write RTL, it must not only function correctly but must also be synthesizable and efficient in terms of speed, power, and area, which is PPA specification. Strong RTL skills open the doorway to advanced concepts like synthesis, static timing analysis, clock domain crossing, verification, and eventually large scale FPGA and ASIC designs. So, remember, mastering RTL is not just a skill, it's the foundation on which professional chip design is built. From here on, we will be moving toward transforming theoretical understanding into real working hardware, one clear and practical step at a time. Make sure to brush up your digital electronics and RTL fundamentals before the next class. It will help you follow the upcoming concept more smoothly. Also, install Xilinx Vivado or use EDA Playground so you are ready because in next video we will jump into the real Verilog RTL coding and implementations. If you are serious about growing VLSI and RTL development, don't forget to like, subscribe, and share my YouTube channel so you never miss an upcoming lessons. And with that, let's continue the journey turning concepts into RTL and RTL into real silicon. Thank you.